Okay, so I think we can start the last lecture of the mini course. So just a recap from yesterday. So basically, we completed this picture of infinitesimal global correspondence. And so maybe it would be appropriate for me to just be clear about the names of contributors to this picture. So as I said, this picture covers more or less, this story from the early 80s to the mid 90s, more or less. So the correspondence between Lie algebras and Poisson Lie groups, I think, goes back to Drinfeld in the early 80s. And then Poisson manifolds and symplectic groupoids. So the connection, started to be investigated by Alan Weinstein and Karasev, I think, more or less, 86, 87, if I'm not mistaken. And there is already a paper by Kos, Dazor, and Weinstein, where at least some of the picture is already clear there, involving the connection between Poisson manifolds and symplectic groupoids. And then there are a couple of papers in the mid 90s by Mackenzie and Shu, where the picture relating Lie algebroids and Poisson groupoids is clarified. Around the same time, the connection between Lie algebroids and Manning triples, these current algebroids together with a pair of direct structures which are transverse inside, was also clarified by Liu, Shu, and Weinstein. And then a bit later, already around the year 2000, or maybe a bit later than that even, there were new insights into the connection between Poisson manifolds and symplectic groupoids, given by Cattaneo and Felder, and then Kreinig and Fernandez, involving these path spaces. This global construction that Rui mentioned yesterday. And I think you more or less see a bit of the pattern here. You often, when you go from infinitesimal to global, if you think about Poisson manifolds and symplectic groupoids, or bialgebroids and Poisson groupoids, you kind of simplify the geometry, right? In the sense that symplectic structures are very simple in particular cases of Poisson structures, but you pay a price, which is that now you work on a groupoid rather than just on a manifold, thinking of a manifold as a very particular kind of groupoid, right? Very simple kind of groupoid. And so what else would I like to mention? And there were, and there were also related works, still I think in the late 90s, basically, exploring a bit the odd dimensional version of these correspondences, namely involving Jacobi manifolds and contact groupoids, and then some work on even Jacobi groupoids by David Iglesias and Juan Carlos Marrero. So I won't really talk about that. So what I want to do today, so basically this is the outline. I would like to talk about multiplicative differential forms in general. So we saw multiplicative symplectic forms on groupoids, and I would like to explain a bit what's the infinitesimal geometry associated with them, give some examples, hopefully connecting a bit of this story with what Anton talked about, and then talk about, if I have time, other things that are being currently done right now. So this story about multiplicative differential forms, so will be mostly based on, I think the way we started understanding it started with a paper that I wrote with Alejandro and Christian, and then we further developed with Alejandro, and there is some parallel work of Marius and his former student Camilo Arias Abad. So this is all related. Okay, so let me just start recalling what the general definition of a multiplicative K form is on a Lie groupoid, right? So just remember what this equation really means. So you have the composable pairs of groupoid elements, and there are three maps. There are three ways you can map this to G naturally. So you can, project onto the first factor you can multiply the two because they are composable, or you can project on the second factor, and this is really an equation here on the composable pairs. So I pull back the form omega through the multiplication to this submanifold of the Cartesian product of G and G, and you should have this equality. So I'll talk more about this equation later on. So for us right now, it's just the working definition, and I mentioned, right, it was an exercise to see that a symplectic group, if the form is symplectic, this equation alone is really equivalent to the original definition of a symplectic groupoid that was done in terms of the graph being a Lagrangian submanifold. So that's my working definition for now. And the simplest example that you can think of, so if you want to produce a multiplicative K-form, for example, you could start, so this is just an example. You could start with a K-form on the base of the groupoid, and then define a form on the total space of the groupoid by pulling back this form by source, by the target, and taking their difference. Okay, so this is always a multiplicative K-form, and probably the simplest kind one can have. So I'll talk more about that later. So there's a cohomological interpretation of this. Just have that in mind for now. Okay, so really what I want to discuss is the infinitesimal geometry associated with it. Okay, so let me go to the definition of the objects that will be the infinitesimal counterparts of multiplicative differential forms, and then I'll give you some examples just to illustrate a bit the definition. So, here's the object that will play a role in the talk. So basically, if you have a Lie algebroid, I'll be concerned with pairs of maps from the algebroid into exterior powers of the cotangent bundle of the base manifold, right? So the maps are mu and nu, and they satisfy, three equations. Okay, so I don't really expect you to understand the meaning of these equations right now, but let me just tell you how these equations arise, or how you could deduce them, at least as related to the problem. So, it's an observation. If you have a multiplicative K-form on a groupoid, then what happens is that if you contract, it's a bit like the business that we did with multiplicative bivector field. So if you contract this form with something that is right invariant, you get something. So now it's a one form, right? But this one form is the pullback of something from the base, right? And this something will be exactly, I'm sorry, I mean, if this was a two form, this would be a one form, but if it's a K form, it's a K minus 1 form, right? So then this guy is in K minus 1 of T star M. So that's what I put back here. And you could get this map nu by doing the same thing with the differential of omega. Right? So it's very easy to see from this equation, right? I mean, just because the differential commutes with pullbacks, that d omega is still multiplicative. Right? So it has the same property. So when you contract like this, you get something that is a pullback now of a K form on the base, and that's what this nu is. right? So these are the equations that define maps, just like I wrote there. And it's also very easy to derive from these equations the equations that these maps have to set. I mean, those equations there. What's not so easy is to know that, or not so evident, is to know that this is exactly what you need, that this is sufficient for you to describe the objects globally. So the theorem, the kind of infinitesimal global correspondence theorem, is, so if you have a Lie groupoid, again, that is source simply connected for you to get this one-to-one correspondence, then there is a one-to-one correspondence, really, between multiplicative k-forms on the Lie groupoid, and this object that, just for lack of a better name, I just called IM k-forms. IM is infinitesimally multiplicative. But on A. So these are just these pairs satisfying those equations. And the relation, at least going from global to infinitesimal, is just exactly what I wrote there. Okay, so before, I probably won't even have time to tell you a bit about the proof, but the proof follows the same spirit of this idea of using Lie's second theorem, basically reinterpreting all these equations as morphisms between tangent and cotangent objects, and then lifting using the integration of morphism theorem that one has for algebroids and groupoids. So, the idea is simple. It involves a bit of technicality, but it's not so bad. And just one remark is that, it's kind of convenient, a very convenient way, which was important for the computation, is to really see, is to really promote k-forms to functions somehow, to multiplicative functions on groupoids. So basically, you can make sense of this groupoid just taking direct sums of the tangent bundle of the groupoid, and you can see a k-form as a function here. And then, by promoting, a k-form to a function on a different groupoid, it's easier. It's a bit in the spirit of super geometry, I guess, like looking at forms as functions. And then things get easier. So just some remarks. Just like try to explain a bit and try to get something recognizable from the equations that this infinitesimal object satisfy. So let me go back to the equations here. Okay, so these are the equations. So let me first tell you what happens in a very particular case. So if the global object, if this multiplicative k-form is closed, then you only need one of the maps, right? Because the other one is about d omega, so the other one would be 0. So then you would have only one map, just this, and satisfying two equations. So the first is this, the minus sign, and the other one these are the two equations that are satisfied in this case. Now you can actually generalize that a little bit, and instead of just declaring d omega to be 0, you could wonder what happens if d omega that you know is multiplicative is of is of this type, the simplest possible multiplicative thing. So then, let's see what would happen. So suppose that d omega is not 0, but is controlled in this way by something on the base, right? And then you look at the equations there, you see that the first one doesn't change, and the second one, you need, this new component will appear. But what is this new component? So it's very easy to see that if you just apply, if you just extract the new component from d omega, in that case, just a simple computation, pretty straightforward to see that this is how this new will look like.
Turn on the light.
Oh. Yeah, I never know if the lights are on or not. Okay, so that's the new in this case, and it's also very easy to show that if this guy's closed, then the second equation, the equation that nu has to satisfy related to the bracket is trivially satisfied, is automatically satisfied. So you don't need that equation anyway, right? So the difference now is that there will be this term, the nu will appear in this equation like this. Okay, so let me put this here so that you can see. Those who have seen the twisted current bracket will probably recognize this term here already as something very similar to that. So let me go a little further, right? So in this case, that d omega is controlled by a form on the base like this, I would just refer to this as, the form omega being phi closed. Okay, so it's closed relatively to phi in this way. So let's go a little further and see what happens just trying to, understand a little better the geometry encoded by this equation. So let's go to k equals to 2, just to simplify matters a bit. Now, what happens there, right, so for k equals to 2, we have now, and let's concentrate on this case. Okay, so we have one map like this, where now phi here is a closed 3 form, right? So these are the equations that this map satisfies, right? And you see that we can reinterpret these equations now naturally. So let's these IM equations, these equations that this map satisfy. So let's look, to do that, let's look at the map, right? So we have this Lie algebroid around. So this is all defined on a Lie algebroid, right? So let's look at the map that combines the anchor and this component here. So let's look at this map. This is a map that goes from the algebroid where? So the anchor takes the algebroid to Tm, while this second component will take the algebroid to T star M. Right? And just like, let's simplify matters a bit more. Let's simplify things a little more. And let's assume that the kernel of this map, of this combined map from A into T plus T star of M is 0. So that, this is a faithful, some kind of embedding of A into T plus T star. So suppose that this is 0. Right? So if you assume this, then you can, just because A is isomorphic to its image inside T plus T star, you can really reinterpret these equations now in terms of the image completely. So what do the equations say? So the first equation, well, I should have numbered them, but too lazy to do now. So the first equation there will just say that the image, so let me call at L be the image inside T plus T star. So the first equation just says that L is isotropic with respect to the natural symmetric pairing that you have on T plus T star. That's what the first equation says. And the second equation, the second, so to say, IM equation, the one involving the bracket of U and V, that equation just says that L is involutive with respect to the following bracket on sections of T plus T star. So how did I write this? Okay, so in a way, so this is what is called the phi twisted courant bracket. So it's just a modification of the standard courant bracket on T plus T star that we saw yesterday. And it's due to Cervera and Weinstein, I guess, in the paper. And so you see, if you just, impose something mild, just that you can really represent this A inside T plus T star in a faithful way, then, the natural reinterpretation of the equations is just, what we saw yesterday. This is almost what I called the Dirac structure yesterday. Except that, there's still the dimension issue. In principle, this L could have, could have less than half the dimension of T plus T star. Right? So just to fix that, I'll just say that if the rank of A equals the dimension of M, then A is really isomorphic through this map rho mu to a phi twisted Dirac structure. Okay, so these objects known as phi twisted Dirac structures, they arise naturally as very particular cases of these objects that I'm calling IM forms when k equals to 2. Okay, so I'm fixing k to be 2. I'm fixing the differential of omega to be something prescribed, and I'm imposing a couple of regularity conditions. Then I get a phi-twisted Dirac structure. If not, I'll get something more general. Okay, it just corresponds to the fact that you have multiplicative forms, that do not satisfy this, and of course these regularity conditions will impose conditions on omega as well. So, so in this context, so you can specialize this global infinitesimal theorem to, for the k equals to 2k. So this was first proven in a paper that I wrote with Marius, Kreinik, Chen-Chan Zhu, and Alan Weinstein, which is a correspondence between phi-twisted Dirac structures and objects known that we called phi-twisted presymplectic groupoids. So basically, the forms that appear there, first of all, they satisfied this condition on D. This amounts to the phi-twisted business, but then there were two other conditions that were exactly the global analogs of these two conditions here that have a reflex on the global side. And the analogs were, so the first one was that, the kernel of the two form was somehow controlled. Maybe I should just erase this for now. So the first was that the kernel was controlled, so it couldn't degenerate too much, right? So this is just this condition, in a way. It's more like the combination of the two conditions are equivalent, but anyway. And the dimension condition was that the dimension of the groupoid was twice the dimension of the manifold. Right? So, yeah.
Intersection is 0.
Yeah. Thanks. Right, 0. Okay. So the kind of multiplicative two forms that correspond to Dirac structures, they are not just any two forms, but they can degenerate in a controlled way, in a way. Okay, so that's the theorem. So let me now tell you, let me give you a concrete example that now will relate this business to Anton's course. So let me give you a very concrete example of a twisted Dirac structure. And then we'll see what the global counterpart of that twisted Dirac structure is explicitly. So this is an example of a phi-twisted Dirac structure. And this is a Dirac structure that will be defined. So I will present it as a particular case of an IM form. So I'll give you these maps, and they will satisfy these regularity conditions. So the setup would be that I'll be on the Lie group with an ad-invariant, non-degenerate, symmetric form. So the Lie algebra is quadratic, as Anton was saying. And I think I have a slide for that. One of the things about preparing slides after midnight is that you don't really remember what you have. So I think I have one for... Okay, so here's what it is. And so let me tell you, so what's the algebroid, right? I mean, to define an IM form, I need an algebroid. So the algebroid is just the action algebroid with respect to the coadjoint action, right? So it's just the product of the Lie group with the Lie algebra, and the anchor is just gives the infinitesimal generators of the action by conjugation. Now, what else? So let me give you this map mu, right? So I'm going to give you a map. So I already told you what this guy is. So the anchor is this. Right minus left, invariant vector fields, and now I'm telling you what this mu is. What? Yes. Thanks. Right, so that's the formula for mu. So it involves the left and right invariant Maurer-Cartan equation. So I think I didn't follow the bad notation suggested by Anton. But and the whole point is that you can directly verify that this mu satisfies these two equations up here. Okay, with respect to a certain 3 form, there is nothing but this Cartan 3 form that Anton also talked about. So I think in my convention I will just tell you what this, it's by invariant, so I'll just tell you what it is for Lie algebra elements, and it's like this. So I don't know if this is the 1 over 12 or 1 over 24.
Probably, I think 2 times 3 factorial, right?
Right, yeah. Well, that's right. So that's the convention. Okay, and then the point is that, so then, you can look at the image of this map, as I did before. And this is one of the cases in which, the rank of the Lie algebroid, of this vector bundle, well, it's just a dimension of the Lie algebra, which is a dimension of the Lie group. So this matches. And also this kernel property is fine. Like this map has no kernel, right? So really this algebroid is faithfully, it's isomorphic as an algebroid to, a certain image here, which is a Dirac structure that I think I also wrote there. So let me just show you there. So that's what it is, right? So it's basically given by these pairs, and this lives inside Tg plus T star G. Okay, so notice that there is this object that we're defining here. So this is now called the Cartan-Dirac structure. I think a nice way to think about this object is really as an analog of the KKS Poisson structure on the dual of the Lie algebra. Okay, so something to really have in mind is that this plays the role, or is some analog of the KKS linear, right, Poisson structure on, so in which way are they analogous to each other? So here, you have leaves which are the coadjoint orbits. And here, you also have leaves, which are the orbits of the algebroid, which are the conjugacy classes of the Lie group. Right? And then here you on each leaf, you have a symplectic form, as Anton explained. And here, on each leaf, you're going to have a 2 form that is, in this case, not symplectic. It's not, in general, not close or non-degenerate. But it's a form that already appeared before in the literature. So if I use this notation for the infinitesimal generator, so it's something like that, or I don't even need this. Just write it like this. With the signs, so this at a point G is just and this is a 2 form, so this 2 form is defined on each conjugacy class, and in a way encodes all the information of this structure in the same way that, the symplectic forms along the core-joint orbits here encode the Poisson structure, the KKS Poisson structure. It's exactly analogous. So this is a form so this is KKS, and this is GHJW. So Groupoids, Hubschmann, Jeffrey, Weinstein. So that's where it appeared first, already in the study of modular space of flat connections. Okay, so now just to push this analogy a little further, so let's push this analogy a little further. So, we know more or less what to expect, right? I mean, it makes sense to integrate this object. So I'm telling you that this object is something that you should integrate. Yeah?
So the KKS form is defined for the rule of any Lie object. Why would that form only be defined for a Lie group with an incarnate unit form?
Because they are not really the same thing. Yeah, so you need this guy, you certainly need this guy to define this. But yeah, you need that.
So what was that? I think half here.
What?
The formula for your forming.
Here?
Yeah.
So it says, let me write it again here. So this omega GHJW of on infinitesimal generators. So these guys generate the tangent to the orbit.
Maybe just lights?
What?
Maybe if you turn the light on.
Right. Better, huh? So this at a point is that's what the form is. Okay? So here, so we have this analogy. So here, with the KKS, and this is with this guy, Cartan-Dirac. And let's talk about, so in the same way that a Poisson structure now we see, it is a piece of infinitesimal information that you can integrate to a symplectic groupoid, and you know in this case what the symplectic groupoid is. So in this case it's just the cotangent bundle of the Lie group, right? But now you can also wonder what the integration of this object is. Right? This is also an infinitesimal object in this picture. So first of all, what's the groupoid that integrates? Right? So the algebroid is just an action algebroid for the action by conjugation. So the groupoid that you get in this case, as a groupoid, is just 2 copies of the Lie group. And it's an action groupoid with respect to the action by conjugation, now to the global action by conjugation. And this, from the theorem, right, from this theorem relating Dirac structures, or phi-twisted Dirac structures, to multiplicative 2 form, that should be a multiplicative 2 form on this groupoid that you get from this procedure, right? So this coincides with the 2 form that appeared in the paper by Anton and Malkin and Myrinken, about where they introduced this notion of group-valued moment maps. Okay, so this form, I'm not sure if I should try to write the formula now, but you can actually, by integrating, you can actually find the explicit expression. It's like no guesses. You can actually compute. In this particular case, it's kind of simple to really, just using invariants, you see what it has to be, knowing the infinitesimal data. And it's something that looks like this. So I'm going to do this. So for an element here, yeah, so I'm going to use the notation for the projections on first and second factors, like this. And so here what you get, so it's this. Yeah, I'll probably write in a way that is not understandable anyway, but I'll just write it. So that's the formula that comes out. So I don't really expect you to understand the formula, but anyway, there is an explicit formula that I think upon a change of coordinates coincides exactly with the one that Anton wrote on the board yesterday on G times G. So, so these forms were the building blocks, right? And then you have to put G, G times G a bunch of times together to get, a form that he would reduce. Yeah.
All right, I don't quite recall. This is the one which has 2 moment maps, right?
Correct. Yes.
Yeah, then upon the change of variables,
yeah, exactly.
Using bad notation.
Right, and using bad notation, you get to the same one that Anton wrote yesterday. Yeah, so this is the form. So he wrote yesterday a form that would make G times G a G times G group-valued Hamiltonian space. And then, if you want to make this. Yeah, so what I'm saying is that, if you change coordinates a bit, here a bit, you get exactly the formula that he was talking about yesterday. And then if you want to turn these into a G group-valued Hamiltonian space, then there is this extra factor that had a name yesterday that I forgot already.
Polyakov-Wigman.
Yeah, the Polyakov-Wigman, this like fusion term. And
I think my formula only had 2 terms. Your formula has 3 terms.
Right.
So there should be some explanation for that.
Right. Yeah. I don't know. I just know that if you change coordinates appropriately, I even worked it out, you get to the formula from yesterday. Anyway, so I just want to say that this formula arises. So Anton yesterday was saying that you should think of this as an analog in the theory of group-valued moment maps, as really the analog of the cotangent bundle. And I'm just in a way justifying it even more, right? I mean, the cotangent bundle is the integration of this, and this is right, and of the dual of the Lie algebra, and duals of Lie algebras are targets of moment maps, right? If you have a theory in which your moment maps take values in Lie groups, and you identify the geometry of the Lie group, right, that is related to this fact, in the same way, I mean, how to make that a bit more precise, so what's the connection between the definition of a moment map and the KKS Poisson structure here, right? I mean, the connection is that the moment map is a Poisson map. And here, in the same way, you identify this Dirac structure here, for which the group value moment map is a Dirac map in the exact same way. It's totally analogous, right? So from here now, you take the target of the moment map, You have an infinitesimal structure there, you integrate it to a multiplicative thing, you get the cotangent bundle. So here you have a multiplicative structure. Now it's a little different, but you can still integrate it because you have the theorem now, and you integrate it to G times G, and you get what should be the analog of the cotangent bundle. Yeah.
I'm not sure I'm allowed to ask such questions, but how is it for Dirac Lie groups? Would you also have such a similar picture?
So I think the question should start with the with the definition of a Dirac Lie group.
Sure.
Right.
Maybe it's included.
Right. So there are a couple of versions in the market. So one version somehow does not include this. It's just about multiplicativity of the Dirac structure on the Lie group in the spirit of Poisson Lie groups. Right? That version, in principle, does not include this because this is not multiplicative in the usual sense. Right? But if you extend a little bit the notion and you allow the map to be not only a Dirac map, but you allow these two forms as part of your story, then you can make sense of this. And this is a recent paper by Eckert, Myrinken, and David Lee Blend. So they wrote a paper about this type of Dirac Lie groups, including this example, and but they have not integrated them.
But would it integrate using your?
It's a good question. I have to think. I have to remember exactly.
Okay.
So it's a kind of twisted Dirac Lie group.
Right, in a way, except that they do things, in an intrinsic way. So somehow, they have a current algebroid over the Lie group, but it's not necessarily split like this. So I'm not sure if this would immediately apply. Yeah. That's a good question, though. So students can think about that. All right, so let me go a little further. Oh God. Okay, so let me just say a few words about, if you wanted to find more examples of this IM objects, these IM forms, this pair of maps satisfying these equations, where would you look for them, right? So I just want to hint, and probably I don't have time to really explain in full detail, but you see, like there's a different point of view, a more cohomological point of view to multiplicative forms. So for any groupoid, there is a certain, there's a double complex called the Bott-Schumann complex of the groupoid that you can write down. And basically, it's a double complex whose, so the cohomology of this double complex is the cohomology of the classifying space in the same way that you have such a thing for groups. So if you have a groupoid, then you can write you get the picture of what. So basically here's something that generalizes group cohomology, and the vertical direction is just the RAM, right? So in any case, so this is a very natural object associated with a groupoid, if you think of it as as a simplicial manifold. And what I want to, so I just want to point out that if you look at the at this horizontal directions, at this differential here, and you concentrate on this column of differential forms on the groupoid, thanks. Oh God. So, these are the formulas for these operators. So you see that the first one tells you, exactly how, I was telling you before, that is the simplest way to produce a multiplicative form on the groupoid. So this goes from, forms on the manifold to forms in the groupoid by taking S star minus T star. That's what this operator here does. Okay? The next operator is written there is a combination of projections and multiplication. Okay? So you see that multiplicative forms are just guys which are closed in this double complex. So that's the interpretation. Alright? And you see, so let's say if this is a K form, it's a K, co-cycle here, but there are more general K co-cycles, right? You could combine the form with something on the base, right? And you could ask these guys to be now closed in the total complex. The total is 0. And then if you do that, the equations that you get are exactly this, and obviously the multiplicativity one. Okay, so these other objects that I was considering before, they are just slightly more general co-cycles in this double complex. Alright, so just to motivate this, so what is this double complex in the case of an action groupoid? So what is this double complex? So this is a double complex that computes the equivariant cohomology of this G manifold. Right? So these multiplicative forms on these groupoids are related to that. They're part of this double complex. Now I'm talking here about giving you infinitesimal information about these forms. Right? So you would expect that if there is something related to equivariant cohomology that only uses infinitesimal information, that it should be related to what I'm talking about. And there is such a thing. There is something called the Cartan model for equivariant cohomology. And in the Cartan model, I don't really have time to write it down. I think I may have a slide. So anyway, so this is what the Cartan model is. I won't try to explain it. Just there is a model, for the case of an action groupoid. There is a model in terms of differential forms. It's actually, polynomials on the Lie algebra with values in differential forms. Which computes the cohomology, the equivariant cohomology of your G manifold. So equivariant cohomology is just a cohomology that wants to be a cohomology of the quotient, and it is if the action is nice, but it sees more. It has more information even if the action is not so nice. If you have isotropies and everything, the cohomology still sees that, right? In any case, I just want to hint at the fact that if you go to the Cartan model, you'll find many examples of these IM forms. And in fact, this integration procedure, is just a tiny part of this more general relation that you have between the Cartan model and this double complex, proving that the cohomology of that model is the same as the cohomology of this model if the group is compact, for example. But there's always a map. And this integration, the integration, the way I explain it here, only really sees this part. It is just a piece of this map. Okay, that's all I want to say. And this picture was, much further developed by Kreinik and Camilo Arias-Abad. It was like part of Camilo's thesis, I guess. It was like to understand this more generally for other groupoids. Okay, so all right. So the last thing I want to mention is just right. So there's a dual picture that is also well known by now, and it's due to Ping Xu and David Iglesias and Camille Laurent. Right? So they wrote a paper basically describing what multiplicative multivector fields are, so I won't really explain much, but this is well understood. So basically, you get operators that generalize the operators defining bialgebroids. So the main difference now is that they are not of degree 1 anymore, but they can be of degree k minus 1. If you're talking about a k multivector field, and unless the multivector field, so if you don't have you lose the fact that the square, it doesn't really make sense, the square, right? So you don't have really, even in the case of bivector fields, in which this is an operator of degree 1, if you don't say anything about the integrability of the multiplicative bivector, you cannot guarantee that d square equals to 0. Okay, so then, they talk about quasi stuff, where like they control a little bit the failure of the Jacobi identity of the multiplicative bivector, in the more or less in the same way, or in some analogous way that you can control the failure for a form to be closed. Anyway, so this is also well understood. So some current stuff. So one thing that I've been involved with now with Tiago and Noah is understanding multiplicative tensors of mixed type, right? So we know the extremes, forms, multivector fields, what the infinitesimal geometries are, but once you combine, you look at tensors that are that have covariant and contravariant parts, you get other kinds of geometry in the picture, things related to like you have connection like elements that appear. And particularly we've been looking, we know now in general what the description is, and in the particular case of Neuhaus operators, you have lots of nice examples of what the infinitesimal geometry is. So something else, so in Utrecht, Ivan, Marius, and Maria have been working on multiplicative forms with values now in representations, and this, interestingly, comes up in their reading of the classical work of Cartan in a way that I don't still understand yet, but looks rather interesting. So, I think they're writing up something about it. So Madeleine, Christian, and Tiago, they've been working on understanding multiplicative. You can talk about other objects which are multiplicative on a groupoid, for example, foliations and distributions. And even in the very original program of quantizing pre-symplectic groupoids, understanding this, these are the polarizations that you would need on symplectic groupoids to carry out this geometric quantization program that was the initial motivation for symplectic groupoids anyway, and leads in some examples that have been worked out, it leads to non-commutative algebras quantizing the Poisson structure underlying the symplectic groupoid. So they've been working, and there's also work of Eli Hawkins about this, like some recent work, and they've been connecting this with representations up to homotopy. And I think there'll be a talk next week by Madeleine where she will talk about multiplicative Dirac structures on groupoids. So there's recent work of David Lee Bland and Pablo Chevera, also about multiplicative things, and they talk about multiplicative Manning pairs and Q-Hamiltonian groupoids. So basically they integrate Q-Hamiltonian Poisson. Now, Q-Poisson manifold, sorry, I got confused with all the Q's and quasi. Right, so quasi-Poisson manifold, they managed to quantize that. So they find a Lie algebroid there, and quantize it and see what the global geometry is, and find these Q-Hamiltonian spaces, on groupoids. Right, and in this business, also the notion of a multiplicative current algebroid appears. Right, I think it already appeared, in the work of Christian a little bit in the beginning, and then in recent papers by Eckhard Meiringen and David Lee Bland, and David Lee Bland just posted his thesis that he finished this year, with a pretty comprehensive account of all this story of multiplicative current algebroids and his work on it. So I guess I'll just stop here. Thanks.